Okay, so good morning, everybody. Welcome to this lecture of today. We are very happy to have Tomohiro Sasamoto from TaiTech, Tokyo Institute of Technology. We are really happy that he made it to be here during the trimester for a month, and he will tell us everything about one-dimensional KPZ equation.
Thank you. First of all, I'd like to thank Christian and other organizers for giving me an opportunity to give this lecture at IHP. I'm not going to talk about everything about KPZ, but some portion of it. So maybe I just really start from the plan of the lecture during the week. Okay, I should use this one. Is it working? No, it's okay. So today I'm going to talk about kind of general facts and some results known for the KPZ equation and related models. Basically, I will use some slides from my previous review talk. So if you have attended my review type talk recently, they are pretty similar. There could be some. And then from the next lecture, I'm going to talk about basically kind of calculations which are used for studying KPZ equation and related discrete models. And for that, after all, somehow random matrix techniques from random matrix theory is key techniques. So first, I'd like to explain about random matrix. This is actually very huge topics, so one can spend the whole lecture on the random matrix, but I will use only 1 hour, so that will be very compact, and there are no proofs and so on. But still, you see the kind of basic structure which appears every time in the KPZ problems in random matrix theory, so I will explain it. Then next, I will explain the current fluctuation for totally asymmetric simple exclusion process, TASEP. So this was a kind of the first breakthrough by Johansson in the year 2000. So random matrix theory and TASEP or KPZ problems are completely different fields from the beginning. But after Johansson found the good connection between TASEP current and random matrix, then they're having a lot of developments since then. So basically, I would follow the Johansson's argument to see how random matrix type expression appears in this problem of TASEP current fluctuation. And the kind of goal is a recent algebraic structure found by Alex Brodin and Ivan Kovin, which is the McDonald process. So this may sound very difficult, I don't know, fancy one, but I think it is true to some extent, but my impression is that the key concept is actually in the Schur process. And once you understand the Schur process, it is much easier to understand at least the definition and some basic properties about the McDonald process. So I would like to explain the Schur process. And actually, this Schur process is very much related to the calculation of Johansson for the TASEP. So I think this is so once you know this looks, I think, much kind of easier to understand what is the Schur process and how it is important. And then comes the explanation about the KPZ equation. Of course, recent developments in the last maybe 5 years is about the KPZ equation itself and some discrete analogs. And there are some nice new formulas and algebraic structures which I would like to explain. So for the KPZ equation, I would use kind of 2 hours. And first half would be about the basics about the KPZ equation. So maybe you have heard that there are some intrinsic problems about the KPZ equation. I will show the KPZ equation, but the KPZ equation looks just fine, but actually mathematically there's a problem to make sense of it. So first thing we have to do is to have a well-defined version of the KPZ equation. So for that, I can mention this is the way you should do in a few minutes, but maybe I think I would like to explain some background about such procedures. And then, then after making sense of the equation itself, then there are still a lot of things to do. And especially the very good thing about the recent development is that one can find very explicit formulas for the height distribution or some moments and etc. And this I want to explain in the latter part for the KPZ equation. But for the calculation, for example, I would like to think about explaining the results for the KPZ equation by using replica methods. But for the KPZ equation itself, there's some, again, difficulty. So we have to treat the diverging series, for example. So this is not good mathematically, but actually for this case, there is a nice regularization procedure. Just we can use the discrete analogs of the KPZ equation. If we take some appropriate scaling limits, they reduce to the continuum KPZ, standard KPZ equation. But some techniques can be upgraded to the discrete setups. So there are several models like ASEP, QTASEP, QTAZARP, and so on, some more recent generalizations. But I think ASEP and this QTASEP or QTAZARP seems rather simple and good models. I would like to explain this. And to calculate several quantities for these processes, the notion of duality from interacting particle systems plays an important role. So I would like to explain this. And then mention a little bit about the McDonald process, how this kind of algebraic structure is related to the problems in KPZ problems. And finally, I would like to explain a little bit about the related topics. Sorry, I didn't say very much, but so T means Tuesday. So this is reserved for, so the lecture is considered, can be as long as 2 hours, right? And I heard that the 2 hours would be too long. I don't know, but but still, maybe what I'm thinking is that maybe first I explain something for about an hour, and if there's a good point for a break, I take break for 5 or 10 minutes, and then comes to the second part, and goes up to 2 hours. It could be shorter sometimes, but up to 2 hours. So this is, maybe of course this may change, but basically I'm thinking about these for tomorrow, Tuesday. This is for, W is for Wednesday, and so on. Right? Okay. And maybe some of you have already attended, but there are longer version of series of lectures by Herbert Spohn. He's not giving the lecture here, but in very close by buildings. There are some overlaps too, but there are also some differences too. So for example, so I discussed a little bit about what he covered in his lecture. So for example, he didn't cover this one, this shear process. And I heard that he explained more about the, how to say, line ensembles. So the structures related to random matrix and time-dependent version of it. But yeah, so. But on Wednesday, he's going to give Wednesday this week, he's going to give his last lecture, I heard, about the KPZ equation. So and you see, I'm also considering to talk about KPZ equation on Wednesday and Thursday, so I'm trying to fit them in a nice way. So, but of course there could be some overlaps, but I hope they are kind of nice complementary ones. So I would recommend to attend his lecture too on Wednesday. And I heard also that Ivan Corbin he has some position here as a Poincaré chair, and he's coming in May, I heard. So of course he's one of the discoverers of the recent McDonald process and so on. So that would be very much related and very useful for you if you're interested. But there should be some differences too. Okay. So today I would like to do some introduction by using the slides. As I mentioned, so the slides are basically coming from my slides which I use for the review type talks. But usually, of course, the time is limited for such talks, so I have to rush. But because this is a lecture, today I would like to proceed rather slowly so that you can ask questions and so on. Okay, is it okay? So this is the plan? Fine, okay. Okay. So I'm assuming that you are not familiar with the KPZ equation. So if you are pretty familiar with that, you can kind of doing something else too. Either sleeping, I don't know. So I would like to start from the question of what is the KPZ equation? So in some sense, especially here, of course, KPZ equation should be well-known object, but first I would like to start from that. And then the interesting question is that, as I already said, the KPZ equation, as it is usually written, is not really well defined. So yeah, I would like to explain a little bit about it. And then, as I also already mentioned, recent development is that, so there are several developments. So making sense of the KPZ equation is also very important and interesting. And last week there was a conference, as some of you have attended. And for example, Antti Kupiainen explained kind of, I think, new way of making sense of the KPZ equation using renormalization group techniques, which is familiar to him. So there are very, very many interesting developments around the KPZ equation, but at least for me, it is very nice to see that we now have very, very explicit nice formulas for the KPZ, for some quantities in the KPZ equation. So this is the thing I would like to explain. And so this is, KPZ equation is a kind of specific model, and we are of course interested in the properties of that. But somehow, of course, we are interested in universal aspects. Of course, each distribution is interesting, but of course, central limit theorem, Gaussian distribution, they play a prominent role, right? In a certain similar way, the Gaussian distribution is replaced in this context by the Tracy-Widom distributions, which first appeared in the theory of random matrix theory. So yeah, this I would like to explain a little bit. And then, so this is, I still think that this is very, very surprising and astonishing that there are very nice compact formulas for the KPZ equation, and there should be some nice mechanism behind it. And this is sometimes called stochastic integrability. But in fact, I don't like this terminology very much. Yeah.
You mean the Tracy-Widom distribution is related to the solution of KPZ?
Which solution?
The Tracy-Widom distribution is related to the solution of KPZ equation.
In some sense, yes. This I will explain later, already today, and in more detail later, on Wednesday or Thursday. So some of you are familiar with the integrable systems? Yes? No. No. Yes. So usually, if we talk about the integrability, there are at least two notions, right? So classical integrability and quantum integrability. Originally, the integral system was found for classical systems. So the famous example is the KdV equation, which is nonlinear partial differential equation. So if it's, because this is nonlinear, it is completely non-trivial to find some solution, but for some nonlinear partial differential equations like KdV equation, somebody found a very nice solution, like, which looks like kind of particle. So these objects, which is traveling, and there are some interaction among them. So they are called solitons, and behind that solvability of such nonlinear partial differential equations, people found very nice structure, which is related to the integrability of the partial differential equations. So usually, of course, we are interested in, if we are interested in, for example, some differential equation, the solution should be written in integral, right? Because this is differential. If it is a differential equation, if we integrate it, we get some solutions. And usually for nonlinear systems, it is difficult, but there are some equations for which you can do that. And because one can get some solutions for differential equations, I think they are called integrable systems. So this is a classical objects, no quantum fluctuations and so on. But actually, this is the theory of classical integral systems are related to nice Hamiltonian structure. And in physics, if you have classical Hamiltonians, you can try to quantize them. And then the question is, what happens for the integrability of the classical systems? And then people found out that there are kind of quantum analogs of the integrability. And they are called quantum integrable systems, and kind of mechanism related to the solvability of the quantum systems are usually called quantum integrability. Then, so actually this is the terminology which Herbert introduced. So now we have, so the KPZ equation is a stochastic object, and they are kind of integrable in a certain sense. So maybe we can say that this is stochastic integrable. These are examples of stochastic integrable systems. It may be fine, but from the point of view of mechanism of the solvability of the systems, it seems that actually the KPZ equations and other related models are similar to the quantum integrable systems. Sometimes there are some relations between our stochastic systems and quantum systems, and by using, not only using, but by using some structures which seems to be associated with quantum integrability, we can study the stochastic processes. So in that sense, this may be a little bit misleading, I think, but still, for quantum systems, we usually handle the Hermitian problems, which has some symmetry in matrix and operator. But for stochastic systems, it doesn't have to be satisfied, and there are some other constraints coming from the probability. And sometimes this plays an important role in studying these stochastic systems. So in that sense, there are some new aspects coming in for the problems related to KPZ equation. In that sense, maybe we can call it stochastic integrability. So last week, Ivan used the word stochastic quantum integrable system. So this is more precise, I think. But anyway, but sometimes you may see this kind of terminology, and yeah, one should have some kind of understanding, I think, of the terminology. Okay, so yeah, I think striking feature is the explicit formulas for some quantities of the KPZ equation and the related models. But of course, we are also interested in the universality issue. As I already said, this is a kind of generalization of the central limit theorem for independent random variables. But and yeah, KPZ equation has been already associated with the universal phenomena for surface growth and some related physical phenomena. But recently, it seems that we have seen a kind of broader region of physical phenomena, where KPZ behavior appears. So this is what Bernard Derrida said when I met him somewhere last year. So yeah, I was explaining some recent developments about this, and then he said that, well, now it's KPZ is everywhere. So this is the situation. So I'd like to explain some of them. Okay, so first I start from, maybe I'm too slow still. Maybe I start from the motivation to study the KPZ equation, so the first motivation. So the KPZ equation was originally introduced as a model equation for studying surface growth. So surface growth is very natural and ubiquitous phenomena in daily life and in various contexts. For example, kind of easiest way to think about it is you just burn a paper or put it in the ink. So then you see that there are two regions, and we are interested in the surface between the two regions, and especially we are interested in how it grows and what is the fluctuations and so on. So this is such example. So maybe it's not really good to see. It is not so easy to see, but this is many snapshots for burning papers. So of course, if you put the usual fire on the paper, it burns very quickly. But maybe one can put some chemicals on the paper so that one can control the speed of the burning. So there are several techniques to study that. There are other examples like bacteria colony, and so on. Of course, if we talk about surface growth, there are many examples. So for example, maybe you are more interested in this kind of beautiful shape. So this is also nice, but this kind of growth seems to be somewhat different from what we are really studying. So we are interested in more kind of simple growth processes like this, but in a more in detail. So we are not only, so for this kind of case, maybe we are only interested in the shape of the surface, but here this looks much more boring, right? So this is almost flat, but here we can study actually not only the shape, macroscopic shape, but also the fluctuations about the average behavior. So this is what we are interested in. So there are several motivations to study surface growth. One is coming from physics, so non-equilibrium statistics of mechanics. Probably you know this. For equilibrium systems, there's a nice principle like maximization of entropy or Gibbs ensemble. So for which you can base on the whole theory. But for non-equilibrium systems, we don't actually still know the general principle for such systems. So we are still trying to study non-equilibrium systems one by one. And surface growth is kind of simple enough, but rich enough. So this is a good example for studying non-equilibrium statistical mechanics. And recent interest is also coming from the, So another interest has been coming from the interacting particle systems. So this is more related to probability theory. So famous book by Liggett also treats the, not really the KPZ equation, but some particle systems which are very much related to surface growth. And recent interest is also coming from the connection to integral systems, representation theory, etc. So in a sense, this is kind of main issue here, but generally there are other interests too. Okay. So to start the thinking about the surface growth, it is, I think, easiest to consider some example for simulation models. So for example, we can consider ballistic deposition model. So this is a discrete model. So we start from flat substrate, and it grows randomly. So some square is deposited at random position, but usually, basically, it goes down up to the point it can go, like this. But if there are occupied positions like this stops here. So if the neighboring site is already occupied, this stops that point. So this cannot go all the way here. So this is already a rule for the stochastic surface growth, and maybe you can type the program to simulate it. And if you do that, you can see the surface growing like this. So this is 3 snapshots for this ballistic deposition case. So this is 100 sites. This is space axis with 100 sites. This is height axis. So we start from the flat initial condition and see how the surface grows. Basically, it grows linearly in time with some velocity, but there are some fluctuations, and this fluctuation is growing, and we are interested in these fluctuations. If you don't know anything about this kind of processes, you might think that the fluctuation should be scaling like square root of t. If there is some mechanism of central limit theorem, maybe you would expect that the scaling, the fluctuation scales like square root of t. But for example, for this process, this simulation model, what you observe is t to the 1/3, not 1/2. So there are some non-trivial things going on. And this is the first indication that there are some interesting things going on, and we want to study it. Okay, so we call this kind of initial condition to be flat case. Okay. So there are various models for which you see the similar behaviors, so 1/3 exponent especially. And so you would think that there are some universal features behind the scene. And maybe it is a good idea to have some nice, simple theoretical model to describe the universal behaviors. And the KP's equation was probably introduced as such a model by Cardan and Parikh-san in 1986. There's another KPZ, so Kunizunis, Polyakov, Zamolodchikov, and they are actually somehow related in an indirect way. But for this lecture, I'm just going to talk about Cardan, Parikh-san, KPZ. So this is, and now this is in a continuous setting, but let us introduce a height variable, h of xt. So this is height at position x and at time t. So the KPZ equation is an evolution equation for this quantity, h of xt. So this is time derivative and some space derivatives and so on. So this is the easiest. So the right-hand side consists of 3 terms. The second one is easiest, so this is diffusion term. So this, yeah. And this is nonlinear term, which depends on the slope rather than the height itself. And if we stop here, this is a partial differential equation, nonlinear partial differential equation. But because we're interested in the fluctuation too, we put noise term here, which is in a standard setting assumed to be Gaussian noise with mean 0 and the covariance given by this. So this is white noise in both space and time direction. There's a simple scaling for this equation so that one can take basically arbitrary values. So for example, we take mu to be 1/2, lambda equal d equal 1. So the KP's equation we handle actually in the following looks like this.
So what if you don't have noise? So threshold for noise.
Without noise?
Don't have.
Then this is a nonlinear partial differential equation, and actually it is known to be equivalent to the Burger's equation, which is a well-known nonlinear partial differential equation.
So with noise, it's totally different.
Totally. Well, of course, some properties of the KPZ equation is coming from that equation, the properties of that equation. But yeah, in a sense, primary interest of us here is the fluctuations about such macroscopic behavior. Okay, so about the KPZ, you should know also this one. So I mentioned that there are at least 2 KPZs, but so if you Google, the most famous one seems to be this one. These are usually in a small character, it seems, but still, so this is German. So our hope would be that we write many papers, and our KPZ becomes much more famous than this. Probably that would be too difficult, too ambitious. Okay. So let me explain a little bit of kind of simple derivation of the KPZ equation. This is not at all mathematical, just a kind of heuristic argument to see how the KPZ equation could appear. So as I said, the basic mechanism may be, so suppose you want to describe the surface growth phenomena, physical one, by using equations, maybe partial differential equations for height function h. So maybe first simple idea would be to take into account the smoothing mechanism. So if there are some bumps, maybe it smooths away. So maybe one can take simple diffusion equation. But of course, as we already mentioned, without noise, there's no fluctuations for the solution. So this is not certainly enough. We are interested in fluctuations. So maybe we can put noise like this. Then this is already a well-known equation. This is now called Edwards-Wilkinson equation. So this is a linear equation in height variable. So you can do anything you want. For example, you can do Fourier analysis to study this and study basically everything you want because this is a linear system. But if you do some calculations, this does not describe the correct behavior of our surface growth. So especially, we don't see the 1/3 exponent for this. Then here there could be other possibilities. The one way of improving the situation is to introduce the nonlinearity. And for the surface growth, actually, there's a simple consideration from which you see that maybe we should put some nonlinearities. So the surface may look like this. And basically, we are thinking that the surface grows in this direction, perpendicular to the macroscopic surface. But we are measuring the height in this direction. So, the growth is in this way, but we are measuring the height in this way. So there are some simple geometrical effects from that. So you see, so by using the Pythagoras or something, so we see this, so surface grows this way, but we are measuring this way. So if you consider this, we see that for this height function, the growth should look like this. And suppose the slope, dxh, is small enough, then maybe we can expand it in powers. Then, so this is a constant term which can be handled easily. So then the non-trivial first term is this one. And actually, this is the nonlinearity which you saw in the KP's equation. So in this way, in a heuristic sense, one can derive the KPZ equation as a physical model to describe surface growth. Yeah. And the KPZ Kawada-Paris-san did some type of dynamical renormalization group analysis, and for the case of one dimension, they observed, for example, the 1/3 exponent. So this is the strong indication that the universal behavior, which we observe in many simulation models, are captured by this simple KPZ equation. So now this universality class is usually referred to as the KPZ universality class, or KPZ class in short. Okay, but still the KPZ equation is a nonlinear equation, so it may not seem so easy to study, but there's a very nice way of changing the problem in our case. So we can use Kohl-Hopf transformation, which is given by this. So instead of studying the height function itself, we simply consider exponential of it, and we call this z of xt. Then we know the equation for h, the KPZ equation. After the transformation, we can try to see what kind of equation this z satisfies. And if you do the calculations formally, then the equation you would get is given by this. So now you see in z, actually this is linear equation. So this is nonlinear transformation, and in a nice way, the nonlinearity in the KPZ equation disappears, and then what you get is this equation, which is linear. So you might think that maybe, as in the case of Edwards-Wilkinson equation, now the problem is basically solved. But the problem is that now the randomness eta appears in front of this variable we want to study, z. So if we have multiplicative, so this is multiplicative noise rather than additive, we have to be a little bit careful. So it's not completely trivial. It's not at all trivial to study this equation still. But still, there are some advantages of this transformation. For example, there's a nice different interpretation for our problem. So you see, so this is second derivative, and this is just a product. So if you know basics about the quantum mechanics, you see that this is the same equation as a one particle problem with imaginary time in a potential eta. So usually potential does not depend on, in many cases, potential does not depend on t, and of course there's a fixed potential. In our case, this potential depends on both x and t, and also this is random. So in that sense, this is a very difficult problem, different problem, but still, at least at the formal level, one can think of this as the imaginary time Schrödinger equation. And actually, if we are thinking about imaginary time Schrödinger equation, it means that this is also associated with some statistical mechanical problem. And in this case, because we are considering one particle in some time direction, it can be thought of as a problem of directed polymer. Direct means this cannot go in this way. So at each time, this should have some position. But anyway, so this equation can be thought of as describing the polymer, directed polymer in one dimension in random environment eta. Okay. And in this context, it is very natural to think about that the polymer starts from some position, maybe the origin. So this corresponds to taking the initial condition for z to be delta function like this. So, but the original problem was the KPZ equation. So we are interested in what kind of initial condition this corresponds. So this is already has some problem, right? So h is equal to log z by inverting this Kohl-Hopf transformation. And then our initial condition for h is log of delta x, which is very, very singular. One way of thinking about it is that we write this delta function in this form, so like this, and if you shrink the width of this function, then if we put some normalization, then it goes to delta function. And in this case, if you, for the moment, if you forget about this limiting procedure, then this is, because this is on the shoulder of exponential, you can think of this as represented height. So this corresponds to the situation. So for the surface picture, this corresponds to this kind of wedge initial condition, right? But after that, we have to take delta goes to the zero limit, which means that we are considering some shrinking narrow wedge situation. So after all, this is a little bit singular, but for finite t, there's no problem. Yeah, so there's some physical interpretation too. Okay, so this side. Yeah. Okay.
Sorry.
Yes? No.
But this transformation would induce infinite in the noise term.
Here?
Yes.
Ah, yes. Yeah, this I mentioned in the next slide. Thank you. Yeah. So maybe I could also mention that so if there's no noise here, right? Actually, for this case too, so you see that actually the problem is reduced to heat equation, diffusion equation. So the KPZ equation without noise is equivalent to the Burger's equation. And actually, it is very, very well known that for the Burger's equation, if you apply the Kohlhoff transformation, this becomes the heat equation, which you can solve. So yeah. And for the KPZ equation, we can do the same transformation, but this multiplicative noise term remains, which we have to handle. And so here I said that if you proceed formally means that we do calculations by thinking that h of xt is just a usual function for which you can apply the usual rules of differential calculus. But of course, h of xt is a random, stochastic one. So we have to be careful about the correction, Ito correction term. And this is related to the difficulty for making sense of the KPZ equation. Okay. So to consider that problem, it is, I think, more useful to switch to more SD, stochastic differential type description. And physically, somehow, I think people use the Langevin type equation, which includes noise, like in the KPZ equation. But if you think more carefully about mathematics, I think it is more useful to switch to the stochastic differential equation. And basically, our noise eta xt should correspond to time derivative of space-dependent Brownian motion, usually called cylindrical Brownian motion, which satisfies this condition. So this delta is the same as the delta covariance in the for the noise in the KPZ equation. But anyway, if you remember, no, I can do that. So we are considering this equation, but so here basically we try to multiply it by dt. So then eta dt corresponds to dV. But here I just write they are just a product. But if we write the equation in stochastic differential, in the form of stochastic differential equation, maybe we have to be careful about the meaning of the product. Here I'm writing by using the cross, but this we have to be careful. But as I said, here we proceeded formally, which means that we didn't care about the correction term. I will explain in a little more later, maybe on Wednesday or something. But if you know about the difference between Ito and the Stratonovich, usually this is associated, the proceeding in a usual way is associated with the Stratonovich product, which is usually denoted by circle. So in that sense, the equation we get from the KP's equation should be interpreted as dot product here. But there's a simple translation between Ito and Stratonovich, which is given by, there should be 1/2 here. So then you can rewrite the equation here by using the Ito product without anything here. Then we get correction term here. Then if you again use this equation into here in a recursive way and neglect the small order terms, then you see that we get dB of xt times dB of xt. But as I said, cylindrical Brownian motion is assumed to be having this covariance. For different x and x prime, we get delta function. But as I said, if we use this formula here, what we get is dB of x times dB of x, which means that we get delta of 0. So this is a divergence you encounter in the KP's equation. So there's difficulty. So yeah. So how do you do that? No, okay. But maybe we can just forget about the difficulty. So after all, the difficulty is not so bad in the sense that maybe we have delta of 0 here, but so for example, physically, there should be no such divergence. And for example, if you consider some discrete model, there's no divergence like that. So maybe we can think of the situation where there is some kind of renormalization behind. And this is just a fake difficulty. Simply omit it. Then we change the way of thinking. So up to now, we have been thinking that we first have the KP's equation, and by using the Kohlhoff map to the problem. And then we had a difficulty. But once we had the equation, then maybe we can change the way of thinking. So maybe we should start from the well-defined version of the polymer problem, and then consider the well-defined version of the KP's equation. So actually, if we omit the delta Z term, we get this equation with Ito interpretation for this product. And actually, this is known to be well-defined mathematically. There's no problem. So for example, if we start from non-negative positive initial condition, the positivity remains forever. So that we can take logarithm of the quantity. Actually, this is what we do for making one way of making sense of the KP's equation. So we start from this equation, which is well defined and have some nice properties, and then define the solution to the KP's equation to be given by logarithm of z. So this is known as the Kohlhoff solution for the KP's equation. And this was first invented by Bertini and Giacomin, long time ago now, 1997 or 8, I think. But anyway, so with this way, we can make sense of the KP's equation. So if you start from this well-defined version of the polymer problem and goes back to the equation for the height function, then what you see is, in some sense, this one. So there should be minus infinity here. So in some sense, so this is the with a certain sense. This is the equation, the KPZ equation, which is sensible. But of course, we have to think about this meaning, and one way of thinking is like this. And probably some of you already know, but the kind of small problem of this way of making sense of the KPZ equation is that we always have to use the Kohl-Hopf transformation, which is nonlinear. So maybe we want to think about some small perturbation for the KPZ equation. Then maybe for that equation, Kohl-Hopf transformation does not work. So then we cannot really do anything. So of course, it would be very nice if there's another way of making sense of the KPZ equation without Kohl-Hopf transform. And as some of you already know, so Martin Heidler found one way of making sense of the KPZ equation without using Kohl-Hopf, using ideas from Rothbard's probability theory and renormalization group ideas. Of course, he also checked that his solution to the KPZ equation is equivalent to the Kohl-Hopf solution, which had been known before. So they are consistent. So as I also mentioned a little bit, last week there was a talk by Kupiainen, and he also explained in a very general scheme, but his approach can be applied to KPZ equation in one dimension too. And yeah, I think that would be another way of making sense of the KPZ equation. But anyway, okay. Okay. Yeah. Okay. Maybe it is a good timing to take a break. Okay. Maybe it's time to resume. Okay. So far, I have already explained about how to make sense of the KPZ equation. But as I already mentioned a few times, so the recent interest for the KPZ equation comes from one of the reasons of recent interest is coming from the fact that we can find very nice explicit formulas for some properties, quantities for the KPZ equation. And our kind of simplest formula should be this one. So we consider the KPZ equation with the Kohl-Hopf meaning, and we consider this special initial condition. So narrow wedge for KPZ and delta for the polymer problem. And with this setting, so we think that there is a solution for the KPZ equation, and this is random, and we are interested in, for example, the distribution of the height, maybe at one position. In fact, we can take arbitrary position, arbitrary one position, but here for simplicity, I'm just considering the point at the origin. So h of 0 not 0t is a solution for the KPZ equation at position at the origin, right? So this is stochastic. And basically, we're interested in height distribution, but for formulas, actually, it is kind of better to state it for a generating function for h in this form. So this is e to the h so this is just a deterministic shift in. But here we put parameter s. Gamma t is simply taken to be t over 2 to the power 1/3. So basically, this is t to the 1/3. So this is characteristic for the KPZ equation, right? And what we found sometime, it's already 5 years ago, is that for this, so this bracket means expectation value. And for this quantity, we can find a single determinant formula like this. And this determinant should be thought of as an infinite dimensional determinant, known as the Fredholm determinant. And for that, we should specify kernel, which is a kind of generalization of matrix element. And for this case, the kernel we see is given by this expression. So this is integral of a product of two Airy functions with this kind of some deformation. Yeah, so the KPZ equation is after all nonlinear and contains stochastic nonlinear problem. So this is non-trivial, but somehow there are some formulas like this, nice formula like this. So there was some question about some generalization for this. So I said that this is for one point. So for example, of course, we are interested in surface. So maybe we are interested in the correlations or joint distribution at different points. But this is already something which we haven't been able to do for the KPZ equation case. So and for the TASEP, for kind of simpler discrete models, actually there is a nice formula for joint distributions too. So we can take some asymptotic limit. So we kind of know the limiting objects we should expect for the joint distribution for the KPZ equation too. But technically, for the moment, it seems difficult. So I show some nice formulas, but there are also a lot of interesting open questions, which you may try to solve. Okay.
So what's the physical meaning of the term in the left?
This one. Okay. Well, at this point, this is just some generating function. So e to the power h is z, right? Well, I will explain this kind of stuff later more, but e to the h is here. See? And the quantity I'm writing over there is e to the, so z, some, it can be written like this, right? So if you define theta by using this guy, and S is parameter, arbitrary parameter, basically. And then you can think of theta here is also an arbitrary parameter. So then this is a generating function. And then in principle, I will explain later, this is the information about this generating function can be translated to the information about probability distribution of z, right? And because h equals z, this is also equivalent to having the information about probability of h, which we want to know. So in that sense, it is also okay to consider this generating function rather than the height distribution itself. But actually, yeah, but basically following this procedure, we can also write down the formula for the height distribution itself. I showed you that formula first because that looks much better. But one can write down the formula for the height distribution itself. So now we have also x here. But this appears in a rather trivial way. So in distribution, h of xt can be written like this. So this is 1/24, which you saw in the previous slide. And this is also the same quantity, gamma t. And most non-trivial stochastic object is here, ct. So, and from the formula in the previous slide, you can see that the distribution function for this random variable ct can be written as this. On the right-hand side, you see some integral e to the something times a difference of Fredholm determinants with this kernel. This is almost the same as k kernel in the previous slide, but with a different sign here. But anyway, basically this formula is equivalent to the formula here. Yeah, I think this is easier. But of course, the quantity we are interested in is this one. So maybe you have to look at both equations depending on the context. Okay.
Sorry, the information in both formulas is the same, isn't it? The information is the same.
Information is basically the same. Yeah. Of course, there are some tricky points about the uniqueness or something, because this is more related to moment problems. Yeah. But yeah, I will explain later. Okay. So this formula looks pretty complicated already, but still explicit and compact enough so that, for example, one can draw the height distribution by using some program like Mathematica, and you can draw figure. And once you write down the formula, so this is the result, the formula for finite t. And then we are interested in large time behavior. Maybe we should be able to expect some universal behaviors, right? This is what we have been expecting. And if you do that, what you get is the C is the trace rhythm distribution. So Ft, so this is distribution for finite t, Ft of S. This goes to the GUE trace rhythm distribution from random matrix theory. So about random matrix theory, I will explain more for the in the next lecture. But here I briefly mention what it is. So, so there are many random matrix ensembles, but here we only consider a very special nice one, known as the Gaussian unitary ensemble, GUE. And so the probability distribution measure for the matrix is given by this e to the power minus trace h squared. For h n by n Hermitian matrix. So this is a measure for matrix. And because there is a square in the exponent of exponential, this is Gaussian ensemble. And unitary because Hermitian is related to unitary transformation. And for this very nice property of the GUE is that one can write down the explicit formulas for the joint distributions for eigenvalues. There are n eigenvalues, capital N eigenvalues for this case. And this is given by this form, where delta of x is the van der Monde determinant, the products of differences, times kind of one particle product, e to the power minus x. So this is, of course, related to this Gaussian nature of the underlying matrix measure. But getting eigenvalues from matrix itself contains some non-trivial, nonlinear transformation, and the effects of that remains as a van der Monde determinant here. And this is squared for the case of the GUE. So we are thinking about random matrix. Then the eigenvalues are also random. Then maybe we can think about the distribution of the largest eigenvalue, x max. Then in average, it is close to square root of 2n. And if you scale this quantity appropriately, then one can consider nice limit. There is a limiting distribution for the largest eigenvalue, and the limit is given by Fredholm determinant. And this is the trace rhythm distribution for the case of GUE. So GUE type trace rhythm distribution. And the kernel here is given by this, so product of integral of a product of two Airy functions. Of course, this is already very close to, for example, this kernel, right? In fact, if you take t goes to infinity limit, so gamma t is just a t to the 1/3. So one can do simple calculations here. Then what you get is this kernel. So yeah, there are small steps, but basically this means that in the limit of t goes to infinity limit, the height distribution for the narrow wedge KPZ goes to this distribution, known as the GUE trace rhythm distribution. Okay, and from the point of view of random matrix, there are other random matrix ensembles. for example, if we consider real symmetric matrix rather than Hermitian matrix here with basically the same weight, Gaussian one, then we can also consider largest eigenvalue distribution. In this case, the limiting distribution is different from F2, and this is denoted as F1 of F1 function and is usually called GOE, Trace-Widom distribution. Okay. Okay, so these are the figures, drawings of the density function for the two Trace-Widom distributions, GUE type and GOE type. Of course, if you look at the shape in this way, this does not look so different from the Gaussians. But of course, for example, the tail behaviors are completely different from the Gaussian. They are skewed, in fact. And there are also some differences between these two. And there's another one called Gaussian symplectic ensemble, and there's also limiting distribution. But I don't think, basically, it doesn't not appear in my lecture. I skip it. Okay, so I showed you the formula. The question is how to obtain it. And in my lecture during the week, I would like to explain the basic ideas and the calculations about how to obtain that. But here I would like to briefly sketch what is the basic idea and the procedure for that. So originally, the formulas I showed you, height distribution and also for the moment, the generative function, they were obtained by using limiting procedure from discrete model, ASIP. So ASIP was kind of, there was nice result by Tracy and Widom again for ASIP, and the result for the KPZ equation was kind of obtained from that at the beginning. But after that, there was a nice re-derivation of the same formula by using replica approach. So I will explain a little bit about this. So the KPZ equation was mapped to a problem of directed polymer, which I call stochastic heat equation. And that was a one-particle problem. Although I said that this is already non-trivial to solve because of the multiplicative noise, one way of using it is that one can apply the Feynman-Katz expression, because this is a one-particle problem. Then for the partition function, there is an expression like this. So this is the initial, so where B of, no, sorry. Or maybe I missed it. So BT is a Brownian motion starting at X. Usually, of course, we put the potential, which does not depend on T. But here, we also put time variable here. Okay, so, and you see that there is a good chance that we can take averages with respect to eta, randomness, first, because the eta is assumed to be Gaussian, right? So basically with some matrix coefficients, but measure for eta is Gaussian, and here the quantity we want to average is in this form, e to the power eta to the power 1. So basically what we want to do this, so this you can do. But this is, if we do that for this itself, then this is just a single moment. But maybe we can think of the power of z to the power n. And this also has the same structure. So eta is distributed as Gaussian. And the average we want to take is e to the power eta. So this is, here we are considering the situation where we have kind of n polymers with the same randomness. And this way of computing the moments, this way of thinking, about the computing moment is known as the replica method, because we are considering n systems. First, we are considering one random system, but we replicate in n times with the same randomness, and consider the moment first. And in this case, in general, actually, if you take the average with respect to the randomness first, then what you get is some n-body problem without randomness. And in this case, this procedure can be done very, very explicitly by using the Gaussian nature of eta, which I mentioned there. Then what is the object, non-random n-body object for our problem? Actually, it is given by this. So this is a little bit maybe not so easy notation, but this is a kind of transition matrix element from 0, 0, 0 to XXX, and with some generator Hn. And for the KPZ problem, this is written down very, very explicitly and given by this one. So here, so this can be considered as a Hamiltonian for n-particle systems with delta potential interaction. So if you know many-body quantum systems, then without this interaction, this is just a free motion of n particles. And here, if you have v of x, j minus xk, that means that the particles are interacting with the potential v. And now the potential is delta, so it means that there are n particles with the potential term given by this delta. And here, for the KPZ problem, we get minus sign here, which means that particles are attractive. For example, if you consider two particles with delta interaction, this is basically equivalent to the problem, one particle problem with delta potential at the origin. If you learned quantum mechanics, probably as an exercise, you solve this one, and then there's a bound state for this, for example. And this is n particle generalization of that potential. Okay. And the good thing about this Hamiltonian is that this is known to be integrable, quantum integrable. So okay. So by solvability, here I mean that one can write down eigenfunctions and eigenvalues explicitly. And then, because our n replica partition function can be written using this object, we can use the knowledge about this. This is known as delta Bose gas. Knowledge about delta Bose gas to get some expression for this replica partition function. And then try to see if this quantity of interest can be written in a nice form. So this is the quantity we are interested. So at some point I showed you that this can be written as a single Fredholm determinant, but now I'm writing down in a different way. So e to the power h is z. So I'm just writing this one as a generating function of z. So this is the formula. And by using the knowledge about the delta Bose gas, we can find n-fold integral representation for this quantity. Then we put that formula here. Then this looks still very, very complicated, but there are some nice algebraic calculations after that. And finally, you can arrive at the single Fredholm determinant, which I showed you before. I will explain more about this in the later lectures, but today, here I'm just mentioning that there is such procedure here. Okay. But in this calculation, there's a serious difficulty, because I say that there's a nice formula for formula for this replica partition function, and then you can see the behavior as n becomes large for this quantity. Then you see that e to the power n behaves like e to the power n cube. If you put that, you see that this is highly divergent. So this summation does not make sense. But I said that we can get the formula, the determinant of formula from this. So the way one does this calculation is that there are some diverging series, but if you do one analytic continuation at some point, then this divergence disappears and one can proceed. And then actually after that there's no difficulty, and one can arrive at the correct formula, Fredholm determinant formula. But for the KPZ equation there is a problem, but actually for the KPZ problem one can do almost the same calculations for discrete models for which there's no this type of difficulties. So in that sense, so there is a kind of rigorous version of the replica calculations for KPZ problems. For the KPZ equation itself, there are a little bit of difficulty. Okay, and for about the discrete models, I already said that there are at least two nice, simple discrete models. So one is the ASIP, asymmetric simple exclusion process. This is particle systems, maybe on a one-dimensional lattice here. So each site is either occupied by a particle or is empty, and each particle tries to do does a asymmetric random walk in continuous time here, and with rate p to the right and with rate q to the left. And there are exclusion interaction among particles, so this cannot hop to the here, this cannot hop to here. When p or q is equal to 0, particles hop only in one direction, and this is called a TASIP, totally asymmetric simple exclusion process. And for this case, there are various quantities we can be interested, but maybe here we are interested in the integrated current at position x and x plus 1. So maybe we consider this position between sides 2 and 3 and count the number of particles. If particle goes this way with plus sign, and if that is in this way, in the opposite way with minus sign, starting from time 0 and up to time t, then this is the integrated current I'm denoting by n of xt. Somehow I started to explain about some particle systems, but there's a very, very simple mapping from this particle process to height surface growth problem. So namely, so suppose you have this kind of configuration of ASIP particles, and then you replace empty site by this slope, occupied site with this slope, then this configuration corresponds to this surface height. And particle hopping to the right here corresponds to the growth of surface here to here. And suppose P is bigger than Q, so there will be net currents to the right, and this corresponds to net growth to the upward direction. So by this mapping, ASIP can be also thought of as a problem of surface growth. And actually, for example, if you do a simulation, you observe the KPZ behavior, like t to the 1/3 fluctuation. So yeah, in that sense, ASIP is also considered to be in the KPZ universality class. And as I said a little bit, actually, if we take some appropriate limit, weakly asymmetric limit of this model, actually this goes to the KPZ equation. And for ASIP, yeah, ASIP as well, there's no difficulty when we do replica analysis. So this is one way of regularizing the situation. And I already mentioned that actually the kind of first solution for the KPZ equation was obtained through this limiting procedure from ASIP to the KPZ equation. Okay. There's another nice model called QTASIP. and also related Q-TAZARP. And this Q-TAZARP was first introduced by Alexei Borodin and Ivan Kovin 4 years ago now. So TAZARP, you know, right? So TAZARP is a special case of ASAP, particles only hopping in one direction with exclusion interaction. And Q-TAZARP is one generalization of it. So for the usual TAZARP, particles hop to the right neighboring site with fixed rate, 1. If there is a particle ahead, of course, it doesn't move. But otherwise, if the target site is empty, it hops to the neighboring site with rate 1. But for the Q-TAZARP, now the hopping rate, the particle hops only on the neighboring site, but hopping rate to the right neighboring site depends on the distance to the particle ahead. So in this case, there are 2 empty sites here. So this hops, the hopping rate of this particle to here is different from 1, and it is given by 1 minus q to the power 2. So in fact, so in general, it is given by this form, 1 minus q to the power gaps to the particle ahead. If we denote the particle positions by x1, x2, blah, 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 then it can be written like this, xi minus 1 minus xi minus 1. Okay, so this is if when q is equal to 0, this goes to the usual TAZARP. Okay. So this is TAZARP dynamics fine. And there is a well-known simple mapping between exclusion process and zero-range process. Zero-range process means that the particle hopping rate depends on the particle number at each site only. So for the case of ASAP or TAZARP, you have to look at 2 sites. But for the zero-range process, hopping depends only on the number of particles at each site. Suppose we consider instead of particles, the gaps, dynamics of gaps for Q-TAZARP. Then, so for example, there are 2 gaps here, 1 gap here. And if this particle hops in this way, then after that, there is 1 gap here and 2 gap here. And this can be also thought of as the dynamics of particles. And this can be represented like this. So if we consider the dynamics of gaps, we consider, again, one-dimensional lattice process. On each side, arbitrary number of particles can come. And hopping rate of a particle to the right is given by 1 minus q to the power number of particles there. So for example, in this case, the hopping rate of this particle to the right is given by 1 minus q to the power 2, 1 minus q squared. And this is a simple mapping between TAZARP and zero-range process. And, and this process was actually introduced by myself and was that a long time ago. And somehow this reappeared in this context as a dual process of Q-TAZARP. And one can also think about the integrated current for this process too. Okay, so this is what I already mentioned. For ASAP and Q totally asymmetric zero-range process, we can.
Sorry.
Yeah.
I didn't see the difference between ASAP and Q-TAZARP.
ASAP, in the case of ASAP, there could be only 1 particle at each site. But in the zero-range process, there could be many, many particles. Q-TAZARP is a version of exclusion process. There are only 1 particle per site. The difference from the usual one is that hopping rate depends on the particle, on the gaps between particles. Okay. For the ASAP and the Q totally asymmetric zero-range process, one can show that endpoint function using the current and the Q parameter satisfies simple n-particle dynamics. And actually, this is a generalization of the replica partition function, which I explained a little bit for the case of the KPZ. And this can be formulated, this fact can be formulated by using a well-known notion of stochastic duality. So this is a kind of replacement for the usual replica calculation for the random system. And anyway, one can use this approach. And for this case, there's no difficulty of divergence for the generating function. And one can arrive at a nice formula for the generating function. OK, and for ASIP, yeah. So for Q totally estimated zero-energy process, we can, there's also a nice way of understanding, but well, basically one can check this duality. But for ASIP, there is also duality, and this is known to be related to UQSL2 symmetry. There are also some nice generalizations recently, but yeah. OK, and so here I just mentioned two discrete models, ASIP and Q-TASIP, or Q zero-energy process. But recently, there are nice unifying processes. So if you attended the conference last week, Ivan gave a talk on nice generalization of these two. But anyway, for these processes, we can show, for example, Planck-Scherrer theorem, which is a basis for getting nice formulas for quantities. OK. OK. So far, I have explained only the results for the narrow wedge, but there are some other generalizations and developments. So for example, from the point of view of the surface growth, one of the most natural one is the flat case. So I explained the ballistic deposition by using the flat initial condition. But this was a little bit difficult, but so about the replica calculation, Rudesar from here, how to say, so ENS, Paris and Calabrese did the calculation, replica calculation. There seems to be some mathematical difficulty, and there are some trial by Altman, Quaster, and others. But this case has not been completely mathematically solved. They found nice formula for ASIP case, regularized case, but as far as I understand, they couldn't really, they haven't been able to do through asymptotics. But anyway, the limiting distribution in this case is kind of known and expected to be given by GOE trace rhythm distribution. You remember? So GOE is the random matrix of real symmetric matrix. And for the narrow wedge case, we get GUE trace rhythm. But for the flat case, we get GOE. So there is a strong geometry dependence for the limiting height distributions. This is a little bit unexpected thing. So from the universality, we expect real universality. So maybe we may have expected that even though we take various initial conditions, we end up with the same universal distributions. But for this case of KPZ equation, the limiting distribution depends strongly on the geometry and the initial condition. And this is the primary two cases. And as I also mentioned a little bit, so I showed you the formula for the one-point distribution. But the natural question is, what about the joint distributions, either in space and time? And there are some replica calculations by Dotsenko and others. We also did a little bit thing. And more recently, Johansson gave some result for the two-time case. It's not given by a simple Fredholm determinant. It still contains some few integrals at least. But the scaling limit was already taken, so that is non-trivial, nice development. But for example, of course, this is coming from motivation for studying physical properties. In that sense, for example, we don't know how to compute, how easy it is to compute the joint distributions from his formula. But still, there are some nice developments for this case too. But still, the situation is not really satisfactory. So there are many open questions. Okay. So this is a kind of generalizations in a kind of physical way. But of course, we can also wonder why such nice formulas can appear for such nonlinear systems. And as I said, basically, the clue is the connections to quantum integral systems. And there we see connections to quantum toda lattice, XXZ chain, and Macdonald polynomials. So yeah, basically this is all related to the KPZ, but in fact, they are connected to many, many nice quantum integral systems. For example, I don't think quantum toda and XXZ are so similar, but in this context, they appear in very parallel ways. Okay. So this is just one slide about polymers. So the connection to the quantum toda lattice was found by Neil O'Connell for a generalization of our polymer in random media, and he considered semi-discrete directed polymer. So our polymer was on continuum setting, right? So the figure for the polymer I showed was like this, and this is basically R, and this is also R, and from here to here, right? But in the O'Connell case, we consider maybe 1 to n lines, and suppose there are n independent Brownian motions on each line, like this, P1, blah, 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 Pn, P2. They are independent standard Brownian motions. And we consider some polymer starting from first line at time 0. And this goes up to some point on this first line and switches to the second at some point, maybe T1. And to repeat the transition to the next one and ends at the nth position at time T. And we consider kind of energy for this polymer coming from the contribution of the first Brownian motion, second Brownian motion, and so on. And in the formula, this is just given by this. So this is a contribution from the ith Brownian motion. So this is representing energy of this discrete directed polymer. Because we are considering exponential to the power beta times this energy, this is partition, and we are considering all possible paths. So this means that this is a partition function for this discrete random polymer. So where beta should be understood as inverse temperature 1 over kBt. Okay. Here I'm just writing this.
And the duration is in what?
Is sorry, yeah, this should be dt1 blah blah dtn minus 1.
So realization is fixed. The partition function is considered for fixed realization of Brownian motions.
Oh, yes, yeah. That's right, yeah. We consider the various paths, but for fixed Brownian motion environment. So this is still random. So this is corresponding to the fact that our z for the stochastic heat equation was random and depends on eta. Okay. Okay, and behind the solvability, kind of for the moment, kind of nicest structure is given by the Macdonald process, I think. And I will explain later about this. a little bit. So about the McDonald process, I don't explain very much, but there's a nice structure related to multivariable orthogonal polynomials. And at the top, there's a McDonald polynomials. And what Ivan and Alexei found is that behind the solvability of the KPZ equation and the related models, there's a measure associated with the McDonald polynomials. And as I said, of course, if we want to study the, for example, QTASEP, we really have to study this one. But to understand the basic structure, it is very useful, I think, to learn about the Shua case. So it is, as I said, McDonald polynomials is a very nice multivariable orthogonal polynomials, and there are kind of hierarchy. On the top, maybe this is the one, the McDonald polynomials is there, but maybe at the bottom, as the simplest one, there is a Shua polynomial. This is just a very simple object which can be defined using determinant. And if you replace P and Q by S lambda, that is the Shua measure. And this has a similar structure with random matrix. And this can be considered as a generalization of that. Okay, and the nice thing about this object is that this contains a lot of good models in the KPZ class, like quantum Toda and KPZ equation itself, and so on. So there are in a sense, two determinants I'm explaining. So maybe first one I showed is that for the KPZ equation itself, if you consider a nice generating function, it is given by a single Fredholm determinant. But for the random matrix, I also mentioned that the joint distribution for the eigenvalues can be written as a product of determinants. One has to be a little bit careful about the differences of these. Once you get a product of determinant structure for the underlying measure, then it is kind of automatic to get the Fredholm determinant result for some quantity. This is a better situation, which applies to TASEP, Shua, and so on. But for the McDonald process, there's no determinant formula for example, for the McDonald. But still, after some calculations and manipulations, we arrive at the Fredholm determinants. So we haven't completely understood the mechanism why the Fredholm determinant for the KPZ equation and McDonald process appears. But yeah, this is the situation. This is still kind of open question, I think. A bit conceptual, but yeah. Okay. Maybe after that, I explain a little bit about something which I don't cover, I think, in the following lectures. But I go briefly first. So far, I have explained about the two cases, so narrow wedge case and flat case. Another interesting case is the stationary case. Physically, after some time, you expect that the situation becomes stationary. And maybe, of course, you are interested in stationary situation, properties of the stationary situations. Mathematically, one can start from the stationary case. And for the case of the KPZ equation, the height is stationary for the Brownian motion in both directions. Sample path maybe look like this. And we do the dynamics of the KPZ equation from this. Then, because this is stationary after time t, this is also a sample from random Brownian motion. But if you start from this one, of course, there are some correlations among these ones. This is something we can actually study for this case. So this is the 2-point correlation function at 0, 0, and xt. And here we are thinking about actually the correlations of slope rather than height itself. While using the replica, we found that there's a nice formula, generalization of the narrow wedge case actually, but which is given by in this form. Of course, I don't specify this, but this is a little more complicated than the narrow wedge case, but still explicit enough. So, for example, we can draw a figure for the 2-point function using the formula. Recently, these people also studied the stationary case without using replica. But I think that was only for the height distribution. But yeah, one can also study the 2-point correlation functions like this. Okay. So finally, I would like to mention a little bit about the universality of these. First universality I mentioned is that the trace rhythm distributions appear in various contexts. So originally it appeared in the context of random matrix theory. And I'm explaining that it appears as a limiting distribution for the height or current in the KPZ universality class models. So somehow, of course, so the Gaussian universality is strong, but there are nice new universal distributions at hand, and they appear in various contexts. Okay. Yeah, and universality of trace rhythm distributions from the point of view of random matrix theory has been better understood now, but we still don't know so much about the universality of the trace rhythm distributions in our context, polymer and the surface growth. So this is the, yeah, very important and open question. And about the universality of, originally I started from the physical motivation, and if you kind of accept the universality, we can expect that the same distribution appears in real experiments. And actually this was accomplished in the experiments by Takeuchi and Sano, and they used liquid crystal turbulences, which has two kind of phases, and they observed the surface growth for circular shape and the flat shape. And first they checked the 1/3 exponent in this way, and then also observed that if you appropriately scale the height, then they observed GUE and GOE trace rhythm distributions in real experiments. Okay, and this was, if you attended the lecture by Herbert last week, he explained this in more detail, but there's another interesting development related to the KPZ universality. So the KPZ equation was originally for surface, and maybe it can be applied to particle systems, but still, basically, the conserved quantity is there's only one. So for example, in the case of the particles, particle numbers are conserved, but there's no other conserved quantities. But for example, if you think about the dynamics of Hamiltonian systems, usually there are three conserved quantities, like energy, momentum, and number of particles. So usually, at first sight, it seems that it doesn't seem to be related to the KPZ, but first, Henk Behring realized that maybe actually some part of the properties of the one-dimensional Hamiltonian dynamics and more some generic one-dimensional fluid systems is associated with KPZ behavior. So for example, maybe one can think of the Fermi-Pastor chain with this potential, which has no linearity. So there are three conserved quantities. And there are three modes, heat modes and two sound modes. And if you focus on the correlations of the sound modes, actually they are related to the KPZ. The heat mode is described by Levy, but this I skip, and there are something. So this is a simulation by using molecular dynamics for the shoulder potential, not FPU. But in this case, for example, you see these kind of peaks, and so this is the peak for the sound modes, and actually this is basically the same shape as this figure for the single component KPZ. This is a striking universality. Yeah. Okay. There are also stochastic versions, but the question is that. Okay. Okay, no. I know. Okay, so but but this is still at the level of the Monte Carlo molecular dynamics simulations. Mathematically, it seems difficult, but this is also, I think, a very good, outstanding problem. But I have already only talked about one-dimensional case, and in my lecture in the following days, they are also only in one dimension. But of course, we can think about two-dimensional case as well, for example. There are not good kind of theoretical results, but rather recently there's a nice Monte Carlo simulation for in the two-dimensional case. So he, in the context of the directed polymer, he did Monte Carlo simulations in two dimension, 2 plus 1 dimension, and he observed that the geometry dependence of the limiting distribution in this case as well. So I explained a little bit about the geometry dependence of the limiting distributions for the one-dimensional case. This has been confirmed, proved mathematically by using formulas. There's no nice formulas for the two-dimensional case, but at least at the numerical level, you observe similar behavior, dependence of the limiting distributions. So I think it would be maybe difficult, but it would be a very nice challenging problems. For example, to show that there should be a geometry dependence in higher dimensions too. Of course, it would be much nicer if we can determine the limiting distributions, but this is much more difficult. Okay. Sorry, yeah. So this is kind of summary, but I already passed the noon, so maybe today I would like to stop here. From tomorrow, I start the more kind of concrete explanations about the details. So as I showed you at the beginning, I start from random matrix theory first, and then come to Tarsep, Shua, KPZ, discrete models, and Magnolda processes. Okay, thank you for your attention.